Okay, this should be a pretty quick little video for us today. And the intention is just to show you a quick property about integrals. You already know that you can split up an integral with the addition of the boundaries, which I'll show you in just a moment. But the other piece is that when we're looking at a question similar to what you see in front of you, the integral from 1 to 5, f of x equals 3. So they tell you a given interval. But then they actually use it in the question where they say, okay, we've got the integral from 1 to 5, the same parameters there, but it says 3 times f of x, and then it continues on with some more of this. There's two different properties that I'll illustrate it in this question, and so I want to address them both. The first of which is, again, you recognize that what they gave you was that the integral from 1 to 5 of f of x. But when you look at the question here, the problem is that this had a 3 in front of it. Well, that can actually be addressed in another way. Can anybody think of what we could do to that 3 to maybe make this a little bit more doable? My hope is that you're thinking to yourself, well, wait a minute, that's just like the distributive property. Does it matter if I multiply then or if I multiply at the end? And it, of course, does not. If you remember when we did the sigma notation of that exact value using Riemann sums, we did that frequently where we would pull out what was in common. Now, the same is holding true here. In other words, I can look at this instead and say, okay, that's the integral from 1 to 5 of f of x. Now, what we have to be careful of here, and I'm going to apply that dx here, is that that 3 does not multiply the whole thing. So this is not equal to this 1 to 5, and put that 3 in front, f of x minus 2x plus 1 dx. The trouble with this one is that what it would be doing is it would be doing the integral of the whole thing and then applying 3 to every term. And it is not the same thing. We cannot do that. But we can break up this integral. If you remember from last chapter, we had talked about the fact that you can even say, hey, we can actually break up this integral into each of the different parts. Now this 2, whether it's in front here or whether it's to the left or to the right of that integral sign, it really doesn't make a difference. But each of these would get that dx. Again, that'd be 1 to 5 of 1. This should look somewhat familiar in terms of our summations and what we would do, because we would break up that sigma notation into the summation of k and k squared and summation of 1 in this case. So that isn't anything different when we're talking about integrals. The rule still applies here. So to evaluate this first part here, we have to use what they gave us in that this equals 3. And so this would be 3 times 3. However, the following parts we would evaluate based on their own integral. In other words, I'm going to actually find the integral of 2x. And of course, how would I do that? That's x squared, evaluated from 1 to 5. And then the next one would be x, evaluated from 1 to 5. You'll notice that this sign minus here is going to make a little issue when we finish here, but just make sure you're aware that that is a subtraction sign in our problem. So what this basically is saying, I'm going to subtract whatever the results are from this integral. And of course, that's 5 squared minus 1 squared. And so that would be 9 minus 24. Similarly, we would have 5 minus 1, or we'd have plus 4. And so to get this relatively quickly, at least to me, I think it'd be easier to group these two together, giving me negative 20. And so I have 9 minus 20 showing me that it's negative 11. And that would be the answer that I'm looking for. So that being said, and basically what this is illustrating here is that these are the two rules that we're dealing with. That if we have c, or some constant times a function, that we can actually pull that constant out in front and do the integral separately. In addition to that, we looked at the fact that you can split up an integral, that you are, in essence, I guess, distributing that lovely sign to both of them. Both of them are being evaluated over the same integral, and that allows us to do that. So what I want to do right now is I want us to look at our homework packets. Give us a second to load up here. I'm going to pause the video until it loads. Now, tomorrow in class, we're going to be doing some questions here, or maybe it's tomorrow night's homework assignment. I'm not quite sure which I'm going to be using, but here we have number 15 that's in those homework packets, and it basically says to use the graph below to evaluate the integrals. So what it's first doing is saying, okay, from 0 to 6, and so you find that area, and that's all well and good. You do the absolute value, and that's great too. Then you look at C, and of course C is basically saying to you, all right, well now you know what that amount is, and I'm not going to tell you what that is because I don't want to steal that joy from you, but whatever this joy is that you find, basically what you're going to look at is separating this, and I'm sorry this is writing quite thick here, let's fix that. My video thing here, I'll put that on there. Sorry, you're just listening to me. Isn't this fun? Okay, here we go. So what you're going to do is you're going to split up this integral to be 0 to 6 of f of x and evaluate that. Well, you've already done so in the previous question. Plus, then you'll evaluate 0 to 6 of 2 dx. And so that requires your lovely little shortcut that we've been talking about. And the same holds true for the ones below here. And so it's understanding that that's what that whole problem is doing, is evaluating each of those different properties. So understand that that's where we're headed with this and how it's going to be applied. So hopefully that's good enough for you. This video is just intended to show those two properties to you. Great.